Welcome to Cincinnati Test Systems Sentinel 3520 Leak and Flow Test Instrument webinar. Today we have Rob Plumridge, who will be presenting the technical details of the Sentinel 3520 along with the SIGPOD. First, who is Cincinnati Test Systems? We're part of the TASI organization, who is made up of 4 divisions: product integrity, assembly and test, package integrity, and flow. CTS is in the product integrity group with our German leak test partners, Anomaly and CTS Schreiner, our data analytics partner, Symmetric, and our automotive test partner, Sierra CP Engineering. TASI is a worldwide organization covering the world and all of our customers. CTS was established in 1981 and covers direct sales and service with application engineering in North America, Germany, the UK, India, China, and Korea. Our sales and service reps are in Brazil, Ireland, Israel, Taiwan, Southeast Asia, Australia, New Zealand, and throughout the United States and Canada. We are the leading solutions provider of leak test instrumentation and turnkey systems, supplying over 5,000 instruments and systems annually. The Product Integrity Group is a global organization as well. We have service support worldwide and based here in North America with direct support in Mexico, Asia, and Europe. We support all industries. If it's in your house, in your car, in your business, and it shouldn't leak product out of it or material into it, we have built instrumentation and systems to test it. We cover all the leak test technologies: pressure decay, vacuum decay, which includes leak and blockage testing, mass flow testing, which is also functional flow and leak testing, and tracer gas applications using helium, hydrogen, and other gases. And that includes hard vacuum mass spec testing, accumulation testing, purge clamshell, and sniff. Our instrumentation runs the range of very simple entry-level pressure decay systems to full instrumentation that can control test stands, conducting pressure decay, conducting mass flow technologies, and also having multiple channel capabilities, and also supports European design. Every instrumentation and system we build is calibrated with leak and flow standards for both trace gas and pressure technologies. And those are manufactured in our A2LA accredited lab. We also supply pneumatic and manually actuated seals for simply sealing ports, ID and OD seals. Those can also be customized for your application, and also CTS can support that with simple custom fixtures. Why choose CTS? We have all the functional capabilities for simple leak testing to the high-tech, low leak rate applications, and we have a staff and experts globally supplying and supporting our customers. Today, Rob will be presenting the 3520 technology and applications, what the 3520 does, where to use it, waveforms, and how they can help you. Also, sample application case studies will be discussed, which include mass flow testing, anomaly part movement detection, corrective algorithms, and temp comp, along with leak test plus, leak tests coupled with other tests, press, part activations, etc.
One of the key differences about the Sentinel 3520 is, instead of being a standalone box, it incorporates with the Symmetric SIGPOD. And the idea behind that is it gives some extra analytics capabilities through waveform processing and feature checks that open up an extra extra features, extra tools that you're able to use to help solve your problems in production. So just going over the technology and applications and where it really fits for our users. So some of the highlights are that it'll do both pressure decay and flow testing. We've done parts anywhere from a few cc's to almost 1,000 liters in volume. So we've really designed it from the idea of being able to solve large volume applications through pressure control. We're able to do control down to 10 million PSI. And that's because with big volumes, we just add to our variables. Bigger parts, bigger variables. Those same changes let us also do tests in small parts, but it gets to be a balance of whether you need that or not. And that's why we have so many products in our family. When we look at the whole Sentinel product mix, it's all about getting the right box for the test. We also have a built-in fast fill circuit, so you can fill those big parts really fast. No external circuits are necessary. And we can customize it for exactly what the test requires. So as I said, basically all the test types you can think of except for differentials. So no differential pressure, no differential mass flow. But we cover that in some other areas. So it depends on what exactly you need. But a few of the highlights are that we can do those mass flow, and we can also do volume verification, because I'm going to talk today about our pressure control and how we do that. One of the important things to think is we can also do flow control with it. So if you have a unique flow requirement where we need very precise control of how much air is going into a part for something like a volume measurement or a valve characterization, we can do that with the 3520 as well. The other key point is flexibility. We, of course, cater to all sorts of markets. As Mike mentioned at the top of the presentation, last month has been full of medical applications where we're doing what we can to assist. But a lot of it also comes from our automotive background, where the production requirements and part validation is some of the most stringent anywhere in the industry. So we take lessons from whether it's automotive, white goods, consumer goods, and we're able to apply that across all industries. And that's really led us to finding some common applications, some sort of qualifiers of where there's justification or the necessity for some of the things I'm going to talk about with 3520. And that really falls down to 3 specific questions that I ask myself when I'm first talking to a new customer or an existing customer with a new application that they don't know how they want to solve it. Is number one, if the specification says mass flow, 3520, because of the pressure control and some of those features, is going to give you the ability to have the best result possible. Now, there's times when we don't need that same sensitivity. Mechanical regulation and things like that are perfectly capable, more than adequate for the result. But usually when I get involved with an application, it's challenging. Somebody's already saying, I don't know if we can do this. How do I solve this problem? And so that's when I want to go to my toolbox and say, okay, I'm going to pull out my most flexible wrench or what's perfectly suited for it. And so if it's a mass flow, I know it gives me the best chance of hitting the gauge R&R, the CGK, any of those specifications that your end customer requires in your performance with 3520. For those same reasons of that control, large volume parts. Like I said at the beginning, and we're going to talk about it a little bit more, large volume parts just multiply the variables that impact our leak testing. So if we have temperature changes, or if we have volume changes, things like that during our test, we're just going to multiply them out, the bigger the part volume is. And then the third category is sort of broad, but I call it advanced leak test for lack of a better term, in that if you have things like a check valve that may move or release during your test, that's going to cause small little blips, or could cause enough of a disturbance in your leak measurement that it would fail or change your reaction, that's where we want to look at this. So the other thing with advanced is, because we couple the 3520 with a SIG pod, we're able to do more than just leak test in a station. The SIG pod is able to do all sorts of in-process tests, from press and torque to functional testing. So a lot of our customers have needs where they'll say push in a cut plug and then want to do leak tests in the same station. We're able to combine that so that you can have cost savings when it comes to integration costs, floor space on your factory floor, all those things that we think about, where we can find some of that cost savings through efficiency of real estate. So whenever I start talking about leak tests and why we want to choose a certain, say, test technique, or whether it's pressure decay or differential pressure decay or mass flow, it all comes back to physics for me. And the nice thing about leak test is that it really follows the theoretical quite well into real world. We all know that lab results don't always follow exactly what happens once we hit the factory floor. But luckily, we know enough about the ideal gas law, PV equals nRT, and how it works, that we're actually very capable at modeling what's happening, because there's not too many variables. So when we start looking at, when we do leak tests, we have a few variables. We have our pressure, we have our volume, and we have our temperature. Those are the things that are going to change. And so we can control our pressure to the part. That's completely on us. GTS, as we're filling the part, we're going to control how much pressure we put in there. Volume and temperature are two variables that fall outside of our realm. So that's where, whenever we think about an equation, we think about what are our inputs, what are our outputs. The more things we can control, and then the things that we measure and correct for, the more precise our outcome is going to be. So it's always a foundation of when I think of when we're having variability in our manufacturing process, whether our results start to change as we're going through our testing, we're getting results that just don't make sense. We all know, we've all done a lot of leak testing in our lives, if we're on this call, most likely, or we've had a problem with it. So temperature is usually the number one thing we go to. Do you have a fan blowing on it? Do you have overhead doors opening? Is it coming out of a washer before you hit leak station? The 3520 has things like temperature RTD probe inputs, so that we can monitor and possibly correct. And we're going to talk a little bit more about temperature correction later. And then we also have things for volume, when we can measure the volume of the part at the beginning of test. The other thing that happens with volume is a lot of our lines now are flexible. We see where flexibility is key because we want model variations, especially when we're thinking bigger parts. You may have one family that has 50 different variations. And so that's where a lot of the times we'll end up to a mass flow test that isn't going to rely on the volume of the part to be able to have an accurate measurement without a calibration, which just gets difficult to manage. And that's one of the reasons why we'll go to mass flow on some of the large volume parts, because often they are variable volume or variable configurations. And so what I want to stress on this is whenever you start having variability in your test, start thinking about, could my P, my V, or my T be changing? Because when we think about the actual physics, and this is the only math I'm going to throw at you today, so don't worry about it too much. But what I did is I went back and I took what to me is a sort of medium regular size part, 50 liters, which can be quite large for lots of people. If I want to induce a 1 SCCM leak rate or simulate a 1 SCCM leak rate in that part, this is the pressure change per second that creates 1 SCCM of leak. So if we think about 10 SCCM or 100 SCCM, just move that decimal point over and we see how small of those changes are that we're actually measuring and detecting in a part whenever we do a leak test. The same with temperature. If we have that degree Kelvin of change per second in the part, we'd see that as 1 SCCM. Same thing, move that over, 10 SCCM, 100 SCCM, and we start to see why we have so much influence due to variability in temperature. Like, I'm going to stress it all the time, and I'm sure all the people you talk to, it's the number one place I go once we look at, are seals good? Is our fixturing holding the part correctly? I start saying, do we have temperature influences? Is that part changing as we test it? Because that's the name of the game, is we want stability. We want a steady state system as we're testing our part. Any changes, we will read or detect as a leak, because that's what we're looking for, right? A leak is just a change in pressure or a measurement in flow as we're testing the part. And so that's where the next thing I'm going to stress about, the sort of the heart of what makes 3520 special is the pressure control. This is a 100-liter electric vehicle battery pack, full tray size, like you would think about in any of the full EVs. And it's flexible. That's one thing to keep in mind, so it's even more challenging. But this shows the standard pressure signal we have during a mass flow test using 3520. So our raw unfiltered is this blue trace, and we can see we're plus minus about 0.00015 psi, which actually, if we put just a low pass filter on it to get that high frequency noise, this is sampled at 800 hertz, we're down at 0.0001 psi filter. And that's over a nice 110 second trace when we were doing a flow measurement. When we get bigger and bigger parts, this gets more and more important. Now, the same thing we said, when we get small parts, this precision can let us test faster and faster. And I'm going to show you one of those examples coming up, because I don't want to say too small or too big. They're just general rules of thumb. The other part along with pressure control that I love about the 3520, as you can see, I'm probably biased because it's the instrument I deal the most with within the family, but it lets us do full data analytics on it. So we take full traces of not just our pressure waveform and our flow waveform, but we measure all the other inputs that we control. So we look at what's our supply pressure, what's our pilot pressure during the test, what's our input current and voltage to all the valves inside, and also importantly, what's our control voltage to our proportional valves doing the pressure regulation. So basically, I know all of the inputs that I have into the system so that I can see if something's going out of control. I can put limits on that. If, say, my input voltage to my proportional valve is too high, I know I might have a leak or something is going out of control. So it's an extra check and balance I can put on. It also gives me really extensive self-test capabilities. So beginning, end of the shift, I can test exactly that everything inside the box is performing correctly. I know exactly what voltage it should be, and I can monitor that long term, so I could see, okay, yeah, this instrument is hitting 10 million cycles. The proportional valve is starting to take a little bit more current to drive. I may want to schedule maintenance for that. So it just gives me extra visibility into what the system is doing if I need it. And it also really helps when we have factories all around the world that we need to support. And when we start to debug, we can say, hey, do you have a results file from it? Let me see what these different control waveforms are doing, and it can help us remotely debug so we don't have to send somebody out into the field to look at it, where we have extra tools to be able to support you remotely, which is one of the nice things. Also, if we're on the network with this, the SIGPOD is actually a Windows embedded platform, or Windows IoT platform. And so we can actually remote into it if the IT departments allow us, so we can provide support remotely anywhere in the world, as long as we can get an internet connection to that SIGPOD, which is very handy, saves plane rides and days of time, which the last month has showed us how important remote access and support can be. So I have a couple sample application studies. Is there any questions so far that have popped up, Gordon? I haven't been monitoring that.
No, that there haven't. So if there are questions, go ahead and send those to me, and we will get those answered.
All right. So a couple sample application studies to go through, just to show some of the lessons learned we've had over the years of doing leak, and where some variations come, and where we've seen advantages and not. The first one is, this is a customer we worked with for a long time, and they had very advanced, actually, manufactured panels as opposed to boxes. And this is showing a 33-liter engine cavity with a 75-second cycle time. And one of the key things is they're both doing flow measurements. The goal was to be able to reduce from 3 parallel stations to 2 parallel stations. There's a whole high volume engine line. And when we first started looking at it, it was, okay, let's do 30 run gauge R&R comparisons. And we're able to get very close results. But where some of the differences come is when you start to look at larger numbers of tests over time. So this is 1,600 consecutive tests. And what we can see is how tight the 3520 results are as far as the waveform compared to the mechanical regulated system. And that comes from from 2 things. One is you can see that the thermal decay on the 3520 was happening a little bit faster. We were flattening out, and that's because we were able to fill the part faster. That high flow circuit within the 3520 did its job. And the second one was just our spread, how wide. And what that is a result of is changes in the actual test pressure over those 1,600 runs. I think this was a full weekend long test, basically just running the same engine over and over in 2 parallel stations, one the mechanical system, one the 3520. And it showed, when we went back and looked in the data, it was variations in what our gauge reference was. So all the instruments we use are absolute pressure system, no matter which Sentinel instrument you look at. And that's because we want to make sure we have an accurate gauge reference whenever we're doing our tests. So when you're doing 14 psi G, it's always 14 psi G, not riding on barometric pressure changes. And this showed how slight changes in temperature and barometric pressure throughout that day of those runs changed how quickly that part actually filled and started thermally decaying, which we were able to take care of because of our better pressure control, which always referenced that absolute sensor as opposed to just built into the mechanical. Now, this was a very stringent test. It was a low leak rate, challenging, but when we were trying to back up and save every quarter of a second we could to get to 2 stations instead of 3, it's where some of that capability pays off. On the same side, we'd have a very small part. So this was a small engine carburetor where, same thing, trying to reduce number of stations, and their specification required a mass flow test. So we're able to look at it, and I'll actually pull up some data from this one so we can show this. What I'm showing you right now is Symmetric Studio software. This is the same software that runs on the data hub that connects to all the Sentinel instruments. So some of the same the things I'm going to show you as far as how we look at waveforms and start to actually analyze our data and use the power of digitization and visualization applies to any of the Sentinel family instruments. So what we had was as we pop this up, we had a 4.5 second flow test where we would fill the part. It was a 1 PSI test, and the whole name of the game is we want to get to a perfectly stable pressure. So we get within 0.02 of a PSI within about a half a second, and really it's about a 1/4 second from when we start our fill. And then when we get into our actual test, we can see we're holding our pressure basically absolutely, which results in a flow waveform that is incredibly stable. We can see how nice and stable it's coming down. And so we are able to get incredible ROI because they're able to reduce their number of stations. And this is where having that pressure control let us shorten cycle time so much. They were doing 20-second tests before in a competitive system. And we were able to take that pressure control along with also monitoring temperature because they're worried about there being a little bit of temperature. We actually eliminated that being an issue, showed that it wasn't influencing, it was more fixturing. But we were able to just minimize their production time. And then if we take that to another extreme, we have a case of more standard test for us, a 50-liter oil cavity this time. Again, trying to minimize station count. If we can get 1 instead of 2 or 2 instead of 3 parallel stations, that's huge costs. Or at the same time, targeting specific gauge R&R values or CGK values. Now this specifically was a engine where we did a test where we were looking at both a 0 leak and a 25 SCCM because we wanted to verify that the system is going to properly check for a leak and not just show us pass fail, but give us an accurate measurement. And so one of the other nice things is we're able to do these characterization studies, and because of waveforms, we can take longer cycle time tests and calculate our leak rate at different intervals. So if I look at this data, and so say my flow offset, I actually have a mean at 25 to 30 seconds measured. So these are 0 leak parts and 25 leak SCCM parts. And I have measurements at say 28 to 40. So I could, I can do multiple checks as I'm doing my runoffs and my verifications and my lab work to justify exactly what my cycle time studies are going to be. I can get all that different information from one set of data, and then afterwards go back and crunch and say, I get my best gauge R&R or gauge R or CGK values, whichever is going to be your number one at X cycle time. And that means I can change along my waveform. For these ones, it could be, say, a 30 to 33 second or 25 to 30 second. Wherever I average that measurement over is going to give me my result. And so we can see, if we look at our flow, here's our two waveforms. We're really pushing the boundaries as far as how fast we can fill and how fast we can test this part. So we see a little bit of fluctuation in our waveforms, but that's partly just due to thermal stabilization. If we look at our corresponding pressure waveforms, here's how long we did a fast fill at 3.5 PSI before our actual test pressure at 1.5. It looks like on this one. And when we actually zoom into our pressure, we can see how stable that is. And so we have that excellent pressure control that just shows us, it tells me that the system's working right. At the same time, we were looking at things like, what's our supply pressure? So we see that our supply pressure is very stable. This is during our fast fill, so obviously we're going to pull down that headroom a little bit more. Then our precision fill, and then once we get into our stabilize, where the part is full, just maintaining that couple cc leak rate. Same with things like our pilot pressure. And these are all things that you don't use them every day, but when you have a problem, when your line's down, you're having production fallout, or worst case, you're having supplier or customer issues where they said, hey, you sent us a bad part. To me, I always think about these waveforms, this extra bit of data, as my insurance. This is my insurance to show that if you ever come back to me and say, hey, there's a problem, I can first of all say, no, I went and looked and those waveforms were good. When we shipped that part, we've done everything we can. Or we can say, as we'll see in one of the next cases, yep, there is something different about that waveform. We will put in the corrective action to make sure that we're checking for it, and we can actually go back, go through all of our waveforms that we have from the past, and identify which parts had that same condition so we can do a targeted recall instead of having to do 1 million parts. We could do 15, because maybe that's all that have that characteristic. And again, saving this data with your regular Sentinel instruments to the data hub, you'd have that same ability. You can go back and you'd say, what was different about this one? Because that's what we're concerned with at the end of the day, right? We want green light passes, but we check because we know there's a possibility for there to be a red light. And we don't know what we don't know until we've been taught it. And it's the school of hard knocks. We have to make that mistake or let something slip through before we can know that it's an issue. And these waveforms will hopefully be that way to do it.
Hey, Rob.
Yep.
We do have a couple questions. First question, you mentioned waveforms and deviations from that. How do you take a measurement and reject for odd waveform indications?
Okay, that's perfect. And actually, I will show you on the next example because it's a perfect example of that. Actually, yeah, this is perfect because so there's a few different ways to do detection of anomalies. Ideally, we have an example to go off of. We need a baseline. We need to make like a defective part or something like that to create that condition. So this is actually a fuel rail, high pressure fuel rail, diesel engine, where there's a check valve in there. And one of the issues is that check valve should never release or never show any flow through it during a air leak test that we're doing, because we're testing a different part of the system. And it also is probably an indicator that there's an issue with that valve. So we want a way to be able to detect it. And the customer is actually open to whether we do a pressure decay or a mass flow test on it. But what we're able to do is when we tested it with a mass flow, we were able to see, and that condition was present, we'd see these nice blips. Nice being relative, we obviously don't want to see them. And corresponding in the pressure waveform, I'll show you how small of a change that is actually in the waveform. What we do in this case, we'd actually do what we call a peak-to-peak check. So we would have our regular measurement for our flow on this, which would just be a mean value over, let me actually go to this waveform so we can look at it. If I look at these flow waveforms, so our normal check would be, say, a mean value across that window. That would be what we report on. So if we're reporting on that and our limit is, say, 7, we'd be fine. Or even if our limit was 6 and we were taking a mean across that whole area, it would get averaged out and we'd pass that part no problem. So what we do is we do that regular mean check for our flow test, and then across that we'd also do what we call a peak to peak. So we'd measure what our peak value from, say, bottom of waveform to top. In this case, it would be, I don't know, a quarter of a SCCM for this blue trace, whereas this green one with that clear condition would have 2.5 SCCM peak to peak. So we characterize the waveform that way. We can also do all sorts of other checks, like things like slopes, areas under the curve, basically any kind of mathematical equation that you could think of how you'd separate out something, we're able to do with the SIGPOD. And if we don't have it built in right now, we can add that as a custom analytical feature for you, actually. And so if we look at this, that's one way we're able to detect this using mass flow measurements, because if we looked at the corresponding pressure decay waveform.
Hey, Rob,
Yep.
and as you get into pressure decay, there is one other question that you may be able to answer, and that is identifying the thermal decay stabilization. You probably have that as a curve.
Yes. So we can look at, here's our pressure decay waveform for that same fuel rail. And remember, we're looking at about 5 SCCM leak rate. I don't remember the volume of this part. But as we look at these waveforms, we see nothing really different about them. But I do know, because I've looked through this data, and it's the same ones I was just showing you pictures of, this 178206 is one of the waveforms that showed that exact same condition that we saw with the flow waveforms. So we can see that tiny little change. It's almost, when we zoom in right on it, it's almost impossible to see. We can do checks on the waveforms here, but it gets into be a signal to noise. So that's why we actually went flow here, because by using a flow measurement, we're able to amplify our signal to noise ratio of the signal we're trying to detect. So it's all about ensuring that we have good separation between good part and bad part. And that's where there's no set rule. There's some good guidelines that we can give you as far as, yeah, we know if we use a mass flow test, lots of times we'll amplify those transient signals. So it makes them easier to separate. But there's all sorts of different processing we can use from, especially our lessons learned from other functional tests and in-process tests that we do that let you amplify those signals. And that's the same thing when we think about one of the ways we do that as well, and it comes into this thermal decay, is when we're looking at our mass flow tests or our pressure decay, we always see the classic exponential decay curve of the adiabatic or the thermal decay from when we fill the part up, heat it up because we compress that air, and then as it dissipates that energy and is absorbed by the part, it drops in pressure because it's losing energy. So there's a few things we can do with that. One is we can actually turn our pressure decay, if we know the volume of the part, into a flow waveform, which I'm not sure if this one was actually set up to do. It was not calculating it. We can actually do basically a running slope, and we can create from a pressure decay test basically a mass flow waveform, which will amplify that feature the same way. And the other thing we can do is we can actually characterize exactly when our part gets stable, so we can look at when the majority of that thermal decay is finished, because ideally, like I talked before, we want the part to be stable. Stability gives accuracy, typically. Now, one of the nice things is that as long as our parts are coming in a steady state, this curve is all driven by physics. It's all, as long as our part's consistent, like the part's the same casting, wall thickness, and weight, and all those things, this curve will be very consistent. It's physics. The math works the same way every time. So we can end up measuring back into that, and we calibrate that out as to either just an offset of knowing that if we go out to when we get a stable reading, like on our flow waveforms, we know that once we get to 80 seconds, 90 seconds on this part, it's basically a stable reading. But if our variability in the measurements was accurate enough based off of, say, a gauge R at 30 seconds, we can just do a linear offset, and then we can just calculate in there. And I feel like, Gordon, I probably got a little bit sidetracked. Did I cover the thermal decay part completely from the question?
Yes, I did. When you showed the whole curve and where the major drop-off was to stabilization, I think that was the best description.
Yeah, and the key thing I want to think about with thermal stabilization in that curve is we're always going to tell you use as much time as possible, because we know it's going to give the most accurate measurements. But you can measure back into this area as long as your process is controlled and there's not variability in, like, your clamping or your part, like plastic bottles or flexible parts. Lots of times we need to get down into this more stable region because there's still enough variability in that movement. And like if the part is on the heavier side or the lighter side of that injection mold, there's going to be variations in how this thermal decay looks to happen, because you also, things like part flexing or expansion will identify the exact same as thermal decay. So that's one of the reasons where it's not a simple answer to say, yes, we can measure during the thermal stabilization point or this exponential decay point. And ideally we get to a stable system, because then you're measuring the actual true leak as opposed to a calculated value. So that was one example of where we do anomaly detection. One of the other examples of where waveforms and looking at these anomalies is really important is when we're actually getting into debug, runoff, equipment verification. And that's where we're trying to debug the station. We can see things in waveform that help us to just get to the end result quicker. So this is a classic example of a station that was experiencing sporadic results. And this is some data this is the worst sets of data that we got as the station got worse and worse over time, showing some of the behavior. And what we were getting, these same blips, like in the last last set of data, all throughout. And so to give you an idea, these are short test waveforms, which is the actual station cycle time was around 60 some seconds And then we also did some long runs to see if the station would stabilize out and whether it was transients or not, what was causing it. And to give you an idea, these were actually parts that had a 0.55 SCCM leak limit. It was actually a prismatic transmission leak test where we had 2 cavities. And so it was a case where the end customer manufacturer is having some issues. The integrator had went through the station. They went, we can't find anything. Maybe 3520 will solve our problems. And so we put them on and we started going through, and we were having some of the same conditions. We saw stability through a lot of it, but we would see these random blips every 10th cycle or things like that. For example, here was 40 runs that we took on the station, and we had one of these events. And so if we were measuring a window of 140 to 150 seconds for our mean, no problem. But if we had one of these sporadic events happen during our test, it would completely throw out the results, gauge R&R wouldn't pass, and we'd fail a part that shouldn't be failed. Because long story short is there are sealing issues. And so there's 2 ways we could correct this. One is we can say, what's our median? We could do extra feature checks to see a peak to peak. Was there a waveform that had those conditions? And we could actually measure how long we can determine where that starts and stops from, say, a threshold crossing. And we could actually identify with the SIGPOD, was it just a sporadic blip that doesn't matter to us? Okay, pass it anyways. Or in this case, we used it more as a debug tool to be able to show that, here, I'll pull up the other set of data.
Hey, Rob.
Yep.
As you're doing this, there was a question that I think will relate to this.
Okay.
Can you plot upper and lower limits on the display, and does it have capability to calculate the plot control limits?
So if I was looking at, say, my mean flow values, here's my raw values. I can show there's my mean, my plus minus 3 sigma. There's my spec limits. On these ones, they obviously weren't set to detect it. They're just wide open. But that would be whatever my control limits were. As far as calculate, the SIGPOD's able to calculate what your plus minus 3 sigma limits would be. And we can also, we have another tool called Engineering Workstation where you can go and do what we call what if, and say, if we change limits, what would happen to our distribution as far as like first time yield and things like that. It doesn't currently do SPC control limits like Nelson rules or Westinghouse, but I can say that that is actually on our roadmap for things that I'll be working on, because alerting and some of those SPC requirements are one of the #1 requests from our customers, because we want to know not just are we having good parts, but are we trending up or down, because sometimes we have very stringent limits and sometimes they're pretty open, but ideally we want to keep tightening them up, right? Because that's the name of the game. We want to make the best parts we can, because at the end of the day, we're shipping to a customer, and yes, #1, we have to meet those specification limits, but #2, all the OEMs, final customers, every year they give Supplier of the Year awards, quality supplier awards, and by tightening up and showing our process is tight, that's how some of our customers have been able to win those, by going above and beyond with tools like this. And so what we were able to do with this one, when we were actually debugging the station, we were able to show that there was no actual cycle or timing to when these events would happen. And it gave us the ammunition to actually go back to the customer and the integrator and work together and say, hey, we need to spend more time debugging it. There is still a sealing issue. And it was a very complex sealing package that we had to deal with. And just really quickly, because I know I'm getting near the top of the hour, I want to cover two more things that come forward a lot. One is temperature compensation. So that's one of the strengths of 3520 is we're able to do temperature compensation for parts that come into a station at a different temperature than ambient or a changing in temperature. With that said, the first thing I'll say is we always encourage doing everything we can to not have to do temperature compensation. It's not a science experiment, but it can be at times because there's so many variables. The more complex the part is, the harder it is to do. If it's a block of just a casting, simple because there's less variabilities. If it's a fully assembled part at just before functional test, there's going to be parts that were at varying temperatures, things like that. But we do it. We have systems in the field that use temperature compensation every day, but it's really an interactive process between us and the customer to be able to make sure that we have an algorithm that works, that can be maintained, and that we're not overly reliant on. One of the more common things we'll do is we'll do temperature monitoring so that as we're actually testing the part, we all know that temperature is an issue. If we start to have failures more than normal, the engineer, the quality person, the technician on the line, they'll learn this stuff too. They'll know, oh, okay, yeah, our part temperature was 3 degrees different than our ambient. We're probably having an issue with temperature. That probably is a good part. Let's just pull aside. We're not going to tear it down. We'll just retest once it cools down. So it can be used a few different ways. The other thing that we're able to do, and this is where we've been spending a lot of time lately, is with large flexible parts and specifically battery packs. The challenge with packs is, for one, they're large volume, for two, they're low leak rate, and three, they're flexible. So it's basically the trifecta of the worst conditions that you want. And so that flexibility is the third unknown, that we already have things to deal with the first two. So we have some tools that tell us if that part is flexing during the test, because it acts like a balloon. And so if that balloon varies in volume during test, it's going to look like a leak. So we have some things to be able to detect how much that volume changed during test and correct for it. And so this was actually an example of battery pack. The blue is uncorrected leak rate, and the red is once we provide that correction for ballooning of the part during test. So that's one of the things. It's hard to give too much information because, of course, this is very competitive space right now, but we have a lot of information and experience that we can help you out with on these specific applications. And the last one is,
Hey, Rob?
Yep.
I'm going to interrupt with another question. It was in combination with the previous question about the controls. Since the upper and lower limits were wide open, how was the tester rejecting true failures?
Oh, so this data right here was, let me see, this probably had, this one, so there was multiple features on this one, and this is actually, the limit on this one was wider open. I have to think back because this was when we were doing all the debug, and I probably had just opened them up because we were debugging the system, and I think if we had failures, the PLC controls would spit the part out as opposed to being allowed to leave it in station. I think that's the only reason why these are all passes. Okay. But yeah, basically if we had our spec limits would have been, here, let me find one that makes more sense. Like if I look at this carb flow test, this should have, yeah, my upper spec limit was 3 on that. again, seems high. This is also demo data, which some people may have opened the limits so that it all passed. But basically, it would just be anything out of the mean. If, say, my spec limits on this part were 0.43, anything above that would be identified as a fail.
Well, 3 cc leak rate is reasonable for liquid applications.
Yep. So yeah, basically any of these features we can change. It's one of those easy to do things. And we can do different pass fail criteria. Typically it's per feature, but we have some customers that we have some more advanced things that if A, B, and C are within this region, then it fails. Or if A, B, and D are within this region, it fails. Things like that, where it's a cumulative calculation. We've also done systems where, combined with like QualityWorks database, again, which Sentinel can send to, we can actually pull results from earlier stations and could add it to a leak rate. So if we had a sub-assembly that leaked at 5 cc's, we could take that limit in at a downstream station, add that to or minus it from our leak rate to get our final value. And that goes into sort of the leak test plus, where we do things like press plus leak in one station, or torque plus. Also things, fuel injectors, that same fuel injector station I showed you at, we control solenoid valves in it, so we can actually fire injectors so that we can depressurize and pressurize the system and watch response times and things like that. So we can add in that leak testability on top of in-process tests or functional tests. And I think I used up our full hour, but any more questions that came in?
So there was a question, I think you just answered it. It was how you use the data hub to connect to other Sentinel instruments and produce those waveforms. And also any examples of how waveforms have helped customers improve their production. Okay.
So as far as connecting the Sentinel instruments to Data Hub or any of our like data aggregators, it's really simple. You basically just need the Bluehost, your Ethernet cable, and on the simplest, it's directly from the Sentinel instrument into the Data Hub. And there's a few like IP addresses and things that you need to set that our documentation is pretty good on. If not, you can give us a call and we can walk you through the process of that. It's pretty simple. And then it'll just feed and stream all that data in automatically, every result. Then from that, we can also aggregate like a whole line. So you can put Data Hub set up to take 5. And we also have software solutions that we can scale that up from there, so that all of your instruments in the plant can go to the one Data Hub, and you can actually remotely access it. So there's a bunch of different options there as to what makes sense for the number of instruments you have and the number of users that need access to that data. So that's the main one. That's kind of how it's a one size fits all, depending on the conversation we have with you, I think is the easiest way to answer that.
Great. So are there any other questions that we can field for you?
Gordon, I just sent you a question. What happens above, I think it's 1,000 liters? Bill, bear with me.
Oh.
If you could look to
Yeah, so I'm going into mine. So above 1,000 liters, the only reason I put that is we just need to have a conversation. There's no physical or scientific boundary as to the size of part we test. It just gets into what are our expectations as far as detectability and cycle time, the bigger the and pressure and all those things. So
and temperature.
Yeah, temperature. So basically, we've done massive parts before, but some of them are reasonable and some are not. It's the same discussion of when is it right to go to a tracer solution. I'll tell anybody, air is a horrible medium to test with. It's compressible, it's temperature sensitive, but it's the best thing we have based off of cost of production, like ROI, all of those different things. It does the job. So it's all about scaling to what your expectations and needs are. So I'd be curious what the part is. So.
Well, thank everybody for their time. I appreciate it. If we didn't have any more, or there's another question there, Gordon, would you please take that before I comment?
I'm sorry, I missed that one.
It came to me privately. The part they were talking about, over 1,000 liters fuel tank for large mining trucks, Rob.
Ooh, I'd probably say tracer. Whenever we talk fuel systems at that volume, although I will say we did fighter jet fuel bladder tests that I'm sure were above that volume. I'd have to go back and look at my notes. And we were successful on hugely increasing their current protocols. So yeah, go down to exactly what's required, but I'm not sure if that off highway would fall under any of the current like EPA evaporation type stuff. But let's have a conversation on that one. I think we'll figure out what's right.
Yeah,
there's a way to test it, no doubt about it.
If there's tracer gas too, you see Jeff McBee's contact information on their cell phone number, email address. He's our global product manager, and also Gordon and Rob could help that as well. If we don't have any more questions, thanks, Rob. I know this took many hours to put together. We appreciate it. And Gordon for moderating. Do have a recording of this presentation that will get out as needed. And thanks to Jose Pablo for reminding me to do that. We have future webinars. Please reach out to us. Be glad for any virtual demos and one-on-ones as needed. So thank you all for your time. We appreciate it on behalf of Mike, Shankar, and myself. Thank you all.
Thanks, guys and girls.
Thanks again, Rob. Yeah, thanks, everyone. Appreciate it.